So let's begin by looking at the chemistry of ethers and epoxides, thiols and sulfides. We begin with the chemistry of ethers. By now you should know what an ether functional group is. An ether group simply includes an oxygen atom that is bonded to two R groups. So this is an ether. You can see an ether. That's right. Now the R groups could be an aryl group, a vinyl group, an allyl group. Right now you should know what an allyl groups look like, right? So all these are examples of the different R groups that could be attached to the oxygen. Of course, we expect that this is not an ether. This is simply an ester. That's an ester. Now, compounds containing ether groups are quite common. Examples include vitamin E, which is an antioxidant, morphine, which is an opiate, analgesic to treat severe pain, and R-fluoxetine, which is a powerful antidepressant under the trade name Prozac. Now let's talk about naming ethers. Now let's begin with the common names. Common names are frequently used, and all you need to do is name each R group and arrange them alphabetically. Okay, and then they will end with the word ether. Okay, as you can see, this example, this would be ethyl, methyl, ether. As you can see, that's an ethyl group and a methyl group, ether. In this case, you have the tertiary butyl methyl ether. See, so it's very simple. All you need to do is name in an alphabetical way. For instance, if I had this see, you can see that this is an isobutyl group, so this is going to be isobutyl, isopropyl ether. See, so you start out with the isobutyl group, then the isopropyl group, and you end with the suffix ether. So that's how we use. Now, when you want to name them in using IUPAC systematic names, okay, what you need to do here is to make the larger of the R groups the parent chain. Okay, while the R group that bears the oxygen or the alkoxys, we call that an alkoxy substituent. Okay, so for example, this is ethoxypentane. The longer chain, of course, is 5 carbon, while the ethoxy is connected to the oxygen. Now, when you want to name ether, we can name them according to the IUPAC way, just like I said not long ago. And recall that when you are naming, you normally abide with this general formula. You begin with the stereochemistry, the substituent, the parent, the unsaturation, functional group ending. In this case, we have stereochemistry, as you can see. There is stereochemistry about this double bond. Right, this is 1 and this is 2. This is 1 and this is 2. So you can see this is going to be E. Okay, that's an E. And then when you go to number, you number in such a way that all the substituents have the least number possible. This is considered to be a substituent. Right, so this is going to be carbon 1, carbon 2, carbon 3, and carbon 4. Okay, so let's remove the priorities for now. So we have carbon 1, carbon 2, carbon 3, and carbon 4. So let's begin to put in the substituents. The very first substituent is, we have a chloro. So this should be 3-chloro. Let me change my pen here. Here is 3 chloro, and then you have 1 ethoxy, 1 ethoxy, okay. And then we have a methyl group at the we have a methyl group at the 2 position. So we have 2 methyl. We have 2 methyl. Then the parent. What's the parent here? The parent here, as you can see, is bute, and at the function, the unsaturation is at the it's at the second carbon, so that's bute 2E. Okay, so that's how you do that. Now here we have a cyclic cyclohexanol, hexanol. So we have a double bond here, and at the 1 position we have a methoxy, and then at the 3 position we have the alcohol. Okay, the alcohol is R. So if we go like this, so that gives us R. So that's basically how that is. Now, structures and properties of ethers. We know that the bond angle of ethers is similar to that found in water and alcohols. Okay, which is about 112 degrees. That's because of these methyl groups, and we expect the hybridization about this oxygen to be sp3. Okay. Now, how do the R groups affect bond? Of course, the R groups will kind of increase the bond angle because of sterics. They are bulkier. So they are going to increase the bond angle. Now, in chapter 13, we learned that due to hydrogen bonding, alcohols have relatively high boiling points. That's due to hydrogen bonding. Okay. Now we know that an alcohol can, of course, have a maximum of 3 hydrogen bondings. Because we have 1 here, we have 2, we have 3, right? On the other hand, when you look at an ether, you see it can only bind to 2 hydrogen bonds. It can only bind to 2 hydrogen bonds because it has only 2 lone pairs of electrons, as you can see. Has only 2, and so as a result, we expect the ethers to have lower boiling points than alcohols. So the ethers will have lower. So the boiling point of ethers is going to be less than the boiling point of alcohols. Yes. Okay. Alright. So let's now look at this trend here. You can see that the alcohol has a much higher boiling point than the ether. See? And the ether has a much higher boiling point than the alkane. You see? However, when you begin, and of course the reason for the higher boiling point for ethanol is because of hydrogen bonding. The dimethyl ether is because of dipole-dipole interactions, while the propane is the London dispersion. But if we look at this comparison here, all these molecules are ethers. So they all have dipole-dipole interactions common to them. So the reason why the boiling point increases is because of London dispersion forces. It's an increasing boiling point due to the presence of London dispersion forces. Now, ethers are often used by organic chemists as solvents. Okay, you learned in Chem 12A that ethers undergo SN2, are used in SN2 reactions because they help to free the nucleophile. Okay, they help to free the nucleophile by arresting the counter ion. So if you have an ether like this, it could arrest the counter ion. It could arrest the counter ion and prevent the counter ion from going back to the nucleophile. So the nucleophile is now free to attack the carbon bearing the leaving group. Okay. Now, so because ethers have relatively low boiling points, they are used, and they're very polar. They're used in organic synthesis, and because they can easily be evaporated after the reaction is complete. Their dipole moment allows them to stabilize charged or partially charged transition states. Of course, we know that. We have it because they have, as you can see, they have partially charged. Sorry, this is negative. They have partial negatives, right? So they have that, and so they are able to stabilize charged or partially charged transition states. They are not protic, of course. They are not protic because they don't have an ionizable proton. So they are not protic, no ionizable proton, right? And as a result, they don't solvate the nucleophile. So do not solvate nucleophiles. If you don't solvate the nucleophile. And if you don't solvate the nucleophile, it means that the ether will be the nucleophile will be free to attack. See, the nucleophile will be free to attack. Now, metal atoms with a full or partially developed partial charge can be stabilized by ether solvents. Okay, for instance, if you have like a grignard, that's why grignards are always prepared in ether, because the positive charge on the magnesium can easily be stabilized by the partially negative charge on the ether. You see, and that is able to stabilize the positive charge on the magnesium. Okay, so you can see that it stabilizes the magnesium, right? And also it does not have an ionizable proton, which we know will destroy the grignard, which can destroy the grignard. Okay, we know that. But if you have an ionizable proton, you're just going to kill the grignard, as we saw earlier. Now, so crown ethers have been shown to form especially strong attractions to metal atoms. Okay, because of the fact that they can use their negatively charged oxygens to hold the metal. You see, you can hold the metal cation H well. Now, note how many carbons atoms separate the oxygens. These are called crown ethers. You see, and that's why you see here we have a total of 12. We have a total of 1, 2, 3, 4. We have a total of 12 carbons and 4 oxygens. Here we totally have 1, 2, 3, 4, 5. We have a total of 15 carbons and 5 oxygens. And here we have a total of 1, 2, 3, 4, 5, 6. See? So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so you're able to have crack a little bit. So the 12 has to be with total number of atoms, while the 4 has to be total number of oxygens. So you have 15 atoms, 5 oxygens, 18 atoms total, and 6 oxygens. And basically that's how you arrive at the name of the ether. And the size of the metal must match the size of the crown to form a strong attraction. And so 18 crown fits potassium ion just right.